So we'll come back and look at some of the other properties of the ketone a little bit later on, but just going to introduce a few more of these functional groups that we're seeing, because a lot of the chemical reactions that we're going to have a look at actually rely on knowledge of more than one functional group. So we're going to introduce several functional groups first, and then from there we'll see how they work together in different chemical reactions. So the next one we're going to have a look at is the aldehyde. So this is where we've got the carbonyl group attached to a single hydrogen. We can summarize this without bonds as CHO. So it's written in this way to show that the hydrogen and oxygen aren't bonded together. So here we can see the description of the aldehyde functional group. Essentially it's just a carbonyl group attached to a hydrogen, and we've got that one R group attachment with those atoms as well. So how would you know if a compound contains the aldehyde functional group? Well, it's going to have Al at the end of its name. So just like the Al at the start of the aldehyde. So instead of being propane, it would be propanal if it had the aldehyde functional group. That's what we can see here in the structure below. So we've got the aldehyde functional group at the end of the compound here, and then we've also got an additional 2 carbons attached, which would be part of that R group. So in total, we've got the 3 carbons giving it prop, and the Al specifies that we've got that aldehyde group at the end there. So would you expect the aldehyde functional group to be in the middle of a compound or at the end of a compound, and why? Well, it's going to be at the end of a compound because it's only got this one R group attachment. So whenever we have a one R group attachment, that means the compound has its functional group at the end of the compound. So one of the better known examples of an aldehyde is methanol. It's also got a more commonly known name for people who aren't doing chemistry. You might have heard of it, formaldehyde. So formaldehyde has a lot of interesting properties, but one thing it can actually do is preserve biological specimens. So if you've got a particular biological sample that you don't want to break down, then you can actually put it in a solution of formaldehyde to ensure that it's going to be preserved. So this is one way that cadavers are actually tried to be maintained so they're not breaking down too much. So although it can be useful, formaldehyde can also be dangerous because it's actually a carcinogen, meaning it can cause cancer, and a tetragen, meaning it can cause birth defects. So if we look at the structure of methanol, we've got the functional group atoms here, and the other attachment, or R group, is actually to another hydrogen. So that means it's only got the one carbon, hence meth, and the L tells us it's an aldehyde. So interestingly, this methanol, aka formaldehyde, is actually present in tobacco smoke. So as people who smoke know, actually putting a carcinogen, or one of many carcinogens, into your body, but also a tetragen. So what other effects can formaldehyde have? Well, it can cause burning, nausea, difficulty breathing, and asthma attacks. So it's a pretty noxious chemical to be putting into your body. So there are other aldehydes with more carbons, so don't really go into these a lot. We saw propanol on the previous slide with 3 carbons, and if it was ethanol, that would have 2 carbons, and one of those would be included in that aldehyde functional group. So the next one is a carboxylic acid. That's the functional group we're going to have a look at, and as its name suggests, it can actually function as an acid. So we had a look at acids and bases in session 6 and saw that acids had the capability of donating H+. So that's one of the key things that we'll be looking at with our carboxylic acid. It has an extra H+, which can be donated to a base in an acid-base reaction. So here we can see the formula for our carboxylic acid, where we've got our carbonyl group and then an attachment to OH. So you can kind of think of the carboxylic acid as a fusion between two different functional groups that we've already looked at. We've already seen that OH is present in the alcohol, and we've seen our carbonyl present in a few other ones, for example, ketone and aldehyde. So if you squish those two together, you get the carboxylic acid, where we've got carbonyl and an OH, and you can write that as COOH if you don't want to show all the bonding. So how would you know whether a compound has the carboxylic acid functional group in it? Well, you could look at the name, and it's going to have oic acid at the end of the name. So the carboxylic acid is actually the only one that has acid in the name of all the functional groups we look at, so that's a bit of a giveaway. So for example, propanoic acid would have the carboxylic acid functional group, and we can see the propanoic acid structure down the bottom here. So where are the functional group atoms as part of that carboxylic acid? We've got it down here, the carbon double bonded to the oxygen, and also that attachment to the OH group. And what about these carbons on this side? What do they represent? Well, those carbons and hydrogens are the attachment to the R group. So because the carboxylic acid is a 1R group functional group, that means it's going to be present at the end of a compound rather than in the middle. So in this slide, we're going to have a look at a few of the common carboxylic acid compounds and where they're found. So first one is methanoic acid. So you can see the structure for this down here. It's just got the single carbon within the structure. It's actually within the functional group atoms, and the R group in this case is actually a hydrogen atom. So the common name for methanoic acid is formic acid, but be aware that this name doesn't tell you anything about the number of carbons, and it doesn't have that oic acid in it dictating that it's carboxylic acid, so it doesn't quite tell you as much about the compound. It's actually quite commonly found in insect stings, in particular bee stings. So it's one of the chemicals that will actually cause a reaction once you get stung by a bee. Ethanoic acid is a very well-known one. It's got a few other names that you might know it as: acetic acid or acetate. So this is where we have a 2-carbon compound that is a carboxylic acid. So we've got the carboxylic acid group on the right hand side here, and then an additional attachment to carbon, which is that R group. So together we've got those 2 carbons, which gives us eth. And the carboxylic acid being present gives us that oic acid at the end of the name as well. So some of you might already know that ethanoic acid is actually one of the main components of vinegar. And it's also one of the main components of a very important compound that we'll see a lot more of in metabolism, which is acetyl-CoA. So acetyl-CoA is essential to a lot of different metabolic processes, and the only difference between ethanoic acid and acetyl-CoA is, well, I'll draw the structure. So we've got a CH3, then we've got our carbonyl group like this, and the OH is actually replaced by an attachment to CoA. So one of the things that the acetate can do is actually it can turn into acetyl-CoA by switching out this CoA attachment, which is a coenzyme A to be specific. We're going to switch the OH group for this CoA, and that turns the acetate into CoA. So acetyl-CoA is one of the components that will be used to begin the citric acid cycle, which is the start of the process, which is a common metabolic pathway to make most of the ATP inside the mitochondria of our cells. So we'll look at that in a lot more detail once we get to the metabolism part of the course. And the third one we're going to have a look at here is the 4-carbon containing butanoic acid. But tells us that there's 4 carbons, and the oic acid tells us that there is that carboxylic acid functional group, and we can see that in the box down the bottom here. Common name for butanoic acid is butyric acid, and it's actually found in butter once it begins to go off. So one of the breakdown products of the lipids inside the butter is actually this short chain butanoic acid. So let's have a look at how the carboxylic acid can actually behave as an acid, as its name would suggest. So carboxylic acid is actually a weak acid. So that means it would actually prefer to hold on to its H plus than give it away. But still, some of the time, the carboxylic acid will behave like an acid and donate its H plus, around 5% of the time. So we can see a reversible reaction down the bottom here, where one of our carboxylic acids, ethanoic acid, is reacting with water. So because ethanoic acid is an acid, then it's going to be the one that is behaving like an acid in the acid-base reaction here. So if ethanoic acid is an acid, what will the water be doing? Will it be behaving as an acid or a base? Remember, an acid-base reaction always has one acid and one base. So that means H2O is going to be the base. So essentially what happens is the hydrogen here, part of it is going to be lost as H plus, and that's going to be donated to H2O. So after this has occurred, we've now got our product compounds. We've got the conjugate base of ethanoic acid, which has one less H plus, and we can see that here. It no longer has a hydrogen or an H plus attached to that oxygen there. It's now O minus. Minus because it has the extra electron. Remember, H plus is just a proton, no electrons. And by water accepting that extra H plus, it's now become the hydronium ion. And it has now one more H plus than water did initially. So by doing this, the ethanoic acid has become the conjugate base, and water has actually become the conjugate acid. So in theory, this reaction is also reversible. So you could have the conjugate base of ethanoic acid reacting with the hydronium ion, where H plus will be donated from H0 plus back to the conjugate base, and that will allow the recreation of ethanoic acid and also water. So let's have a look at an animation now to have a look how this acid-base reaction takes place. So initially we've got our ethanoic acid with its H plus, and we've got water, H2O. So the first thing that will happen is the H plus will detach from ethanoic acid. So you can see the result of that. We've now got an oxygen that has the extra electron, and we've got a separate H plus. So that H plus will then move over onto the base, which is the H plus acceptor, and that allows the formation of our products, which is the hydronium ion with the extra H plus, and also the conjugate base of ethanoic acid, which has one less H plus. So this is like any other acid-base reaction. We have an acid donating the H plus to the base, and that converts what was the base into a conjugate acid, and what was the acid into the conjugate base. So that concludes part one of the session. So let's quickly review some of what we've been through. So we saw that the hydrocarbon derivatives were composed of carbon and hydrogen, as well as other atoms like oxygen or nitrogen. We saw quite a few compounds that contained oxygen just then. And then we had a look at the carbonyl group, which is where we had a carbon double bonded to oxygen, and that carbon needed to form two additional covalent bonds. So the carbonyl group itself is not a functional group, but we did have a look at lots of different functional groups that contain the carbonyl group. For example, the aldehyde, ketone, carboxylic acid that we've had a look at, all of these functional groups contain that carbonyl group as part of the functional group atoms. So for the ketone, it was a 2R group functional group that contained the carbonyl group as well. And because of the 2R group attachments, it meant that the ketone group had to be in the middle of the compound. Also, a ketone compound will have "-one" at the end of the name. For example, testosterone contained multiple ketone functional groups and hence the "-one" at the end of the name, or something like propanone as well. For an aldehyde, it has a carbonyl attached to a hydrogen and only one R group attachment. So that means that it can only attach to one carbon chain, and hence it will always be at the end of a compound or at a branch point. And we know a compound has the aldehyde functional group if it has Al at the end of the name. Something like propanal or methanal had that Al at the end of the name, signifying that there was the aldehyde functional group. And the carboxylic acid that we just looked at, that was where we had the carbonyl attached to an OH group. So kind of a fusion of a few of the different functional groups we've looked at, having the alcohol group and the carbonyl group together there. And that also had just the one attachment to an R group, and hence it's going to be at the end of a compound rather than in the middle. Oic acid at the end of a compound's name tells us that it has a carboxylic acid functional group within that compound. We saw methanoic acid, ethanoic acid, which is also called acetate, and propanoic acid as some of the examples, and butanoic acid as well. And the last thing we looked at there was the fact that carboxylic acids actually behave like weak acids, being able to donate their H+ to a base around 5% of the time.